we have a curve t comma t squared, and we want to find the arc length. I'm just writing down s over the interval t goes from 0 to a, where a is just some positive number. So I want to keep this general, this parameter a general, just so that I can plug in any value of a that I want to find the length after we get our final answer. Okay, what do we know about calculating the length of a curve like this?
The square root of the sum of the squared derivative values, the vector.
Okay, good. So I do need to find that. What's v of t?
1 and 2t.
Good, 1, 2t. And then I need to find the length of that.
Integrate from 0 to a.
Okay. Yeah, let's just go ahead and say we're integrating from 0 to a of what?
Square root of 1 plus 4 t squared dt.
Yeah, good. This is the magnitude of the velocity. So remember, you're just integrating speed. Rate times time gave us distance, and then when we added those up and took the limit as the delta t goes to 0, we got an integral of just the speed. Good, so this is the integral that calculates the speed. What do you think about this integral?
You could do it.
Yeah, it depends on how long it's been since you've taken Calculus 2, probably. You can do this, you can work this out. What's the first strategy that comes to mind when you see this?
Use it.
Okay, good. The first thing that I think of when I see something like this is u substitution. If I'm thinking of u substitution, I would want the stuff on the inside to be u so that it would make this integral easier. But if I do that, am I going to be able to solve this using u substitution? Why not?
You need an external t variable.
Yeah, good. If I take the derivative of u, it would give me 8t, and there's no t out here to be able to handle that. So I'm not going to be able to do u substitution to finish this. So what's another strategy that could possibly work there?
Integration by parts.
Okay, integration by parts. Usually we have, so integration by parts, remember, is the reverse of the product rule. So usually we have a product when we're doing that. You can introduce an artificial product and, for example, choose one of your factors to be 1 and try to work it out. That might work. What other methods come to mind? I'll give you a hint. What was one of your least favorite methods from Calculus 2 for solving integrals? That involved square root of something squared plus something else squared. Yeah, we can do this with trig substitution. Typically, students don't enjoy trig substitution very much.
Tan.
Okay. All right. So let's actually walk through this because it's good to have a refresher on this. That is a useful method. I do want you to be able to do it. So let's say we have sine squared theta plus cosine squared theta equals 1. I'm going to want something that has a constant plus a trig function squared equals another trig function squared. And I can't get that using this equation because I would have to subtract and I would have 1 minus trig function squared. So if this was a minus, I would use this equation. But since it's a plus, what do I need to do?
You can use the tangent squared because tangent squared plus 1 equals secant squared.
Okay, good. I need to use tangent squared. if I don't remember the equation for tangent squared, it's really easy to get it from this one. What do I do? How can I make a tangent squared somewhere in this equation?
You could possibly divide everything by cosine.
Yeah, good. I can divide everything by cosine squared, and then that turns the sine squared into a tangent squared. So divide by cosine squared. This turns into tangent squared. This turns into 1. And this turns into secant squared. This will work for us. We've got 1 plus a trig function squared equals another trig function squared. So once we've identified this, now there are different ways to go about finishing up the problem. What do you guys want to do to try to finish this up? What would you do next? We'll take a 5-minute break after we finish this problem.
You said tan theta equal to 4t, 2t.
Okay.
So, yeah, you said tan theta equal to 2t.
Okay, and what will that accomplish for us?
Take derivative of it.
Okay, we will do that. And this is a good choice. But I just want to make sure that everybody's clear on why we would choose this. This.
4t squared and tan. That's what they.
Okay, good. This choice is essential. You can make this choice in other ways, like you could say t equals tangent over 2 or something like that. But this choice is essential to finishing the problem, or a choice like it. What this accomplishes for us is that now this 1 plus 4t squared is just 1 plus tangent squared, which is secant squared, and the square root of secant squared is just secant. So this turns into the integral of secant. That's what it accomplishes for us. And then this dt introduces some extra stuff that we'll have to handle as well. But that's where we're going with this. So John, you said then take the derivative of tangent. So if I take the derivative of this with respect to actually, how do you want to take this derivative?
I think with respect to t.
Okay, so let's divide both sides by 2 and then take the derivative of both sides, or take the derivative of t with respect to theta. How about that? So 1/2 tan theta equals t. Now I can take dt d theta. And what is that derivative?
1/2 secant squared theta.
Okay, good. Derivative of tangent is secant squared. If you don't remember that that's the derivative, or you're not quite sure you have it right, you can write tangent as sine over cosine and use the quotient rule just to make sure. Check yourself. Now, how can I use this?
You plug it into that equation. So if you know that 2t is equal to tan theta,
Uh-huh.
then 4t squared is equal to tan squared theta.
Okay, good.
So 1 plus tan squared theta. And then the dt, you have dt up there. You
Okay.
have secant squared. Plug in the 1/2 secant squared theta for dt. So you get 1/2. That times 1/2 secant squared theta. Since you know that 1 plus tan squared theta is secant squared theta.
Okay, hold on. Let me stop you real quick.
I'm going ahead.
All right. This dt turns into 1/2 secant squared theta d theta. So I'll plug that in here. And then we'll simplify this. How about this 0 and the a? What do you want to do with those?
Because they're in terms of t. You
Okay.
have to change up to in terms of theta.
Okay, good. We can rewrite them in terms of theta, or if we want to, we can keep them in terms of t, and after we find the integral in terms of theta, we can go back and plug in the t's for it. Either way is fine. For now, I'm just going to say these are t values. And then when we simplify, we can do it however we want to. So altogether, since this turns into secant squared, like we said earlier, the square root just gives us secant. We've got the integral of 1/2 secant cubed. Do you guys remember integrating secant cubed at all?
Yeah.
Okay.
So,
It's a little bit complicated. How have you done it?
take square root, so secant squared theta
Mhm.
times secant,
Yeah.
and then secant squared is 1 minus 10 squared theta.
Okay, so we're thinking of secant cubed as secant squared times secant. And then secant squared, we know from that equation over there, is 1 plus tangent squared. Before we start to handle this, do you want to keep the bounds in terms of t, or do you want to change them to theta values?
Either one.
Okay. If we change them to theta, what will the top bound be?
It would be tan theta equals 0. So
Okay, so for this bottom one, if you plug in t equals 0 into this equation,
yeah,
tan theta equals 0.
So 0. No, pi over 2. Pi over 2 is
Okay. At pi over 2, sine over cosine is 1 over 0.
fine. No, it's 0. Y over x.
Good. The sine over cosine, or y over x here, is 0 over 1. So that would be theta equals 0. What about for t equals a? If I plug in t equals a here, what's theta?
Inverse tan on 2a.
That's right, it's just inverse tangent of 2a. I'm going to write the antiderivatives. I'm going to write all these integrals without the bounds, and then we'll just put the bounds on it later. Okay, so for those of you who are helping me to walk through this, what do you want to do next?
Distributes.
Okay, distribute secant. And then what can we do now?
Well, you can integrate secant theta.
Okay, good, yeah.
So you just separate them. Which is a secant theta.
We can separate them. Oops. Do you remember the integral of secant theta? It is something, it's one of the ones that you should probably have memorized, but it's not hard to go back and figure out what it is.
It's the secant x. Secant theta tan plus tan theta.
Then we can't take a secant theta tangent theta.
times tangent theta. The derivative is secant times tangent.
Yeah, I was mixed it up.
Here, let's work out the antiderivative of secant real quick. There's a little trick that you can use, if I remember it correctly. Oh, let's represent it as secant. So the little trick is to multiply it by 1 in a special way, and then you get secant squared plus secant tangent on top, and just secant plus tangent on bottom. Use a U substitution. U equals secant plus tangent. And then what's du?
Secant theta, tan theta, plus secant squared theta.
Good. Times d theta. So if you take the derivative of secant, it's secant tangent. Derivative of tangent is secant squared. And now secant times this numerator is secant squared plus secant tangent. So this antiderivative turns into the antiderivative of du over u, which is?
Natural log of u, natural log of secant theta.
Good. Natural log, absolute value of u, and then you just go back and plug in what u is. So the secant plus tangent was close. And by the way, if this is very painful for you, I can completely, I can feel your pain. This was definitely my least favorite type of stuff to do when I was learning math. I do want you to be able to walk through something like this. All right, now what do we do with this piece? I think we need to use an integration by parts here. Don't we? Isn't there an integration by parts somewhere in this process? I mean, maybe we need to change the tangent squared first. I don't remember. Say it again. Okay, so you can definitely think of this as secant tangent times tangent. And then, how can we use that to help us get to where we want to go?
Integration by parts, u equals tangent, dv equals secant tangent.
All right, let's see. Let's see if that gets us somewhere. What would du be?
Secant squared.
And what would v be?
Secant theta.
Okay, good. So we're just rewriting this piece right here. What does integration by parts say that we can do with this? What does this turn into?
UV plus integral 3 times.
Okay, tangent secant minus the integral.
Secant times secant squared.
Okay, and we still have this other stuff out in front. I don't have space for it, so this dot 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 is secant plus tangent. Okay, good. We are getting somewhere here, so that did help us. How is this going to help us?
Is it 1 plus tan squared theta secant squared theta?
Is what? I'm sorry, say it again.
Is it 1 plus tan squared theta secant squared theta? Or
Yes, that's true.
You can plug that in for secant squared.
Okay, we could plug that in here.
Yeah. But it never, I don't think it ever ends.
Okay, good.
So then for it never ends, then you can end up back to the original.
Okay,
And
good.
then combine the integrals and then divide by whatever coefficients you have in front of the
Good. We came back to, this is sometimes called like the loop method or something like that. We came back to an integral that we started with. We started with secant cubed. Now we have a secant cubed on the other side of the equation. So remember what we have here is that this is equal to 1/2 integral of secant cubed. And now we subtract 1/2 secant cubed, or I'm sorry, add 1/2 secant cubed to both sides. So this is the integral of secant cubed plus c. We wanted 1/2 times that. So to get to our final answer, we're going to have a 1/2 out in front. And then we have an option. We can either go back and plug in everything in terms of t and then plug in 0 to a, or we can plug in the bounds in terms of theta here. I am inclined to rewrite everything in terms of t and plug in t equals 0 and t equals a, but it's fine to do it the other way as well. If we were going to plug in t values, what would secant of theta be and what would tangent of theta be? Let's see if we can remember what we had. I think we chose tangent theta equals 2t, right? So we know what tangent theta is. What's secant theta?
1 plus 2t.
Say again?
1 plus 2t.
Okay, why do you think it's 1 plus 2t?
You have to legitimately change.
Yeah, what's the relationship between tangent and secant?
1 plus tangent squared theta plus secant squared.
Good. So if I want secant, I can just take the square root here.
Or t squared.
Good. There are issues of plus or minus here that I'm sort of glossing over. But secant theta is the square root. And we need to evaluate all of this from t equals 0 to t equals a. And that would give us the length of that curve. Before we stop, before we take a 5-minute break, what does the graph of that original curve look like? What was the r of t?
T squared.
T and t squared? Okay. So if x is t and y is t squared, what's the relationship between x and y?
Plus
It's like an exponential.
It's more simple,
x squared of x.
almost. X is t and y is t squared. So what's y in terms of x?
X squared.
Yeah, it's just x squared. X is actually equal to t. So this is just the length of a parabola from t equals 0 is the vertex. And then as you go out to the right, this just calculates the length of that parabola.
So is that how you show that the trajectory of the segment of the parabola? Because you have t and t squared, so
Yeah, that's right. I'm just looking for something like this to show that the trajectory is a parabola. Yeah.